Recording is rolling. It is Monday, February 3rd. All right, so a bunch of you guys just turned in your harmonic motion waves quiz. We grade those soon. All right, rotational dynamics quiz. Most of you guys turned this in about 2 weeks ago. Now, I do want to give those to you guys, but I've been having a bunch of students this year not turn stuff in or turn it super late. So if I don't get this by Wednesday, then I just have to leave a zero in the book so I can get everybody else's quizzes back to them. And then you guys can do corrections and all that too, which I know a lot of you guys are waiting to get that quiz back so you can do corrections. So definitely double check double check your focus. Make sure you got this quiz in. Most of you guys do. Not everybody does. Right, and by Wednesday, if it's not in yet. All right, so I have a few demos for you guys. Then we'll do a Kahoot, and then I got some more demos. So, of course, normally I like to do the stuff before the quiz, but just kind of how things pace out is a little bit weird. And then, then we'll try to put a close on this topic and start new stuff later. Tomorrow, we're supposed to do resiliency during fifth period, right? I didn't see any indication of a modified schedule or anything like that, so I guess we're doing that in class, and then I don't know, I'll figure out what to do at the time there. All right. Oh yeah. You guys remember those mental health lessons from past years? Yeah. So I know in the past that they've had like a bunch of those like periodically. I think the way they're doing it this year is we're just doing it tomorrow. I think. Yeah. So. All right. All right. So yeah, there's a lesson up there. All right. What have I got for you guys? All right. Let's do a little review here. So you guys know past couple weeks we've been looking at like wave type motion, so oscillation and waves. Okay? And you guys saw these two different categories of waves. I showed you guys a video version of these, but here's the animation. Okay? So longitudinal and transverse. Ooh, and you guys remember longitudinal? Like if I tape a little red flag to that slinky right there, you see for longitudinal, each individual particle moves left and right, and the energy propagates left to right also. That's parallel. Right? But in transverse, it's like the opposite situation. If I tape a little red flag right here, you guys see that red flag is only going to move like up and down, and then the energy propagates left to right, which is perpendicular. Okay. So, what do you guys think light is? Do you guys think light is transverse or longitudinal? Transverse. Light is transverse, and I can show that to you guys because I'm going to show you guys a video version of this. These polarizing filters. You might possibly have polarizing sunglasses, or maybe the light from your computer screen might be polarized. If it's polarized, light gets through in one direction. So if this is polarized vertical and vertical, then okay, most light goes through. That's right. But what if I take one of these and turn it 90 degrees? Ooh, do you guys see how no light gets through? Right? Because if it's vertical versus horizontal, all the light gets blocked. But it only works for transverse waves. So that right there is evidence light to be transverse. And actually, what light ends up being is just part of the electromagnetic spectrum. So it's oscillating electric and magnetic fields. What do you guys think sound is? How are you guys hearing me right now? Sound is a what kind of wave? Longitudinal. Like a pressure wave, right? Sound's a pressure wave. Right? Does sound need a medium to travel through? Yeah, yeah. Like sound cannot travel through a vacuum. Light can, which is good because that's how sunlight gets to Earth through the vacuum space. But the sound needs a medium because it's a pressure wave. I can show that to you with a Rubens tube. Oh, whoops. Let me. I gotta mute this Kahoot. Hang on, because we got two different sound files going at the same time. I know you guys are waiting for Kahoot. Let's put the pause on that. Gotta mute that one. Let's get this other video going. Rubens tube. Well, okay.
Planes, little bit of oscillation from the vibrations in the hose. As you can see, this sets up a standing
Ooh, you guys hear that sine wave?
wave, and we can see what.
Ooh. Okay, so yeah, it's like really robotic, just clean sound, just like a sine wave. Okay. Now you guys know sound is a pressure wave. So see if you guys can make sense of this. Is this point right here, is this a high pressure or a low pressure point? High, because it's pushing the flames down. Okay. What do you think is vacuuming the waves up? What? What kind of pressure? High or low? Low pressure. So you guys see it goes low, high, low, high, low, high, pressures. Right? Okay. And because if you knew the distance between these points, like say from crest to crest, you could sort of figure the wavelength, right? And you're hearing the sound tone, so that could be the frequency, and put it all together. What is wavelength times frequency? That gives you the what? The speed, right? Wave speed. Right? Speed is wavelength times frequency. All right. How about this? What if he changes the tone?
the emerging sine curve that's shaping the sound. We can see.
Ooh, do you guys see that frequency go up? Is if you increase the frequency, what happens to the wavelength? Decreases. What happens to the wave speed? Stays the same. Stays the same. Right? It's the same speed. Right? A higher frequency is a smaller wavelength. You guys just saw that? Speed is wavelength times frequency.
Time we set up a standing wave, we get that sine curve.
All right. Uh, let's look at some standing waves, and then we'll do Kahoot. Save some of these demos for later. It's a standing wave. Now, not all waves are standing waves, but could be. Right? You can't have standing waves. Okay? All right. Ooh, you see it's just going up and down, and there's a couple nodes where the hands are that are not moving. Is that? Ooh. Right, and the different kind you can set up. Guys, take a good look at that right there. How many wavelengths do you see right there? How many? Yeah, one. I see one. Okay, because that right there is probably the most fundamental that you can get for one wavelength. That shape, you could copy paste that shape right next to it itself, and it could make a nice smooth wave, right? But you couldn't do that with anything shorter. Right? So that'd be like one wavelength. That's one wavelength right there. Because what if I touch that right in the middle? So you guys remember where my mouse cursor is right there? If you reach up and touch it right there, let's zoom back a little bit. Can it still bounce up and down? Yeah, I think that might be a Kahoot question coming up pretty soon too. Right? Actually, this point right in the middle is called a what? Starts with an N. No, node, right? And how about this point right here? Could be a antinode, right? So we got looks like go back. We got 1, 2, 3 nodes and 1, 2 antinodes. Is that right? How many wavelengths right there? Yeah, okay, 1.5. Yeah, there's one full S shape and then another half. Do you guys see a node right there and a node right there? And then if you include the hands, that could bring you up to 4 nodes, right? And I see 1, 2, 3 antinodes. This could be your crust and your troughs. Okay? How many wavelengths right there? 2. We got 1, 2. 2 full wavelengths. You guys that? 2 wavelengths. Okay? Let's go way back to the beginning, way back here. Because this one right here, this is probably like if you have a stringed instrument. If you have a piano, it's you hitting it with the hammers, or if you have a guitar string, it's probably looks a lot like this. One of your thumbnail poster notes says guitar string, and throw this picture on it. This the picture of what's going on. This could be a string vibrating up and down. How many wavelengths is that right there? Well, here, if I zoom forward a little bit, I remember this right here was one wavelength. You guys remember that? That's one wavelength. Okay. So if I go back to here, how many wavelengths is half a wavelength? Yeah, right. That's half a wavelength. To get the full wavelength, you need 2 of those, right? Well, one's upside down, right? Okay. To make the full wavelength. Right, you guys got that? So that's half a wavelength right there. And then on your poster notes, it follows there too. Shit. Let's see if I can dig that up real fast before we start the Kahoot. Notes. I got it right here. I switch my screen over and show this to you guys. Point. Here it is right here. Hey, is that half a wavelength right there? It's a standing wave too, isn't it? Standing wave, half wavelength. Okay. It's right here, all the way at the bottom. You see, wavelength would be twice the length of that string. That's right, because this is half a story. The other half story would be out here if it was right. So that's what's that box right there. It's just said that. All right, I think it's Kahoot time. Just ready for Kahoot. Let's get the sound going right here. Here we go. The pin is on the board. Get in. I think you guys are all ready. The time needed for a wave to make one complete cycle is. Let's see the time needed. Yeah, is one time period or a period. Yeah, so how much time? And how could you measure time? You measure time in what unit? Seconds. Yeah, how many seconds? Okay. How about the distance it travels during that time period? That's called one what? One wavelength. So wavelength is in meters, that's a distance. Time period is in seconds, that's the time. Yeah. All right. And then, whoever picked frequency, You guys know frequency is the reciprocal of time period, so it's related. If you know one, you can know the other. But that's the reciprocal. Right. All right. You guys good with time period? All right. We got Zariana, Zach, Luciana. Got some points. That sound is an example of a longitudinal. Okay, so that's a pressure wave, right? Longitudinal pressure wave. All right. Got Elise, Isabel, Zariana, Luciana, Zach. When two or more waves, same place, same time, the resulting effect is called. Oh yeah, there you go. Interference. You guys know this? Constructive interference, destructive interference. Right, like noise canceling headphones were destructive. Right. Okay, so yeah, you can either add or sort of subtract the amplitudes from each other. They're upside down. Right. Interference. Interference. All right. Got Ian, Jonathan, Zariana, Luciana. Zach. Ooh, where can you touch a standing wave on a rope without disturbing the wave? At a node, right? At a node, right? You touch it at a node, right? Because that point doesn't really move, so it wouldn't disturb the wave. At a node, all right. Standing waves can be set up. Yeah, all the above. Yeah. So now one of these examples is transverse. Guys, which of those examples up there is transverse? How about how about a string that's vibrating on a musical instrument? Be transverse, right? And then blowing across the top of a bottle or organ pipes, those I think would be more longitudinal, right? Oh, hey, how about the lab you guys did last week with the PVC pipe in the water? Right, that was kind of like this red and blue answers there, right? Which could also be standing waves, right? So different kind of waves, but they could be standing waves, right? In your lab last week, that version, maybe there was a constant high pressure point right above the water line, right? Okay, so like a sort of think of it like a node, right? All right. Suppose a bug jiggling up and down and swimming towards you at the same time. Compared to the frequency that the bug is emitting waves, the frequency that the waves reaches you is blip, 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 blip. Should be a higher frequency, right? This bug swimming towards you. It's the same. Let me find my poster version of this. Do I have? Guys, that's called the what effect? Huh? You said Doppler, right? Doppler effect. All right, it's got to be. Here it is. Here it is. Took me too long to find that one. All right, got Doppler effect right here. Let's switch over. Boink. Okay. So this is the animation you guys were just looking at. Okay. So guys, if that bug, if this is a bug in the water going bleep, bleep, bleep. Okay. Now, if it wasn't moving, the water's not moving, then these wave ripples are reaching you, also like bleep, bleep, bleep. But if the bug is swimming towards you, you guys see that the waves going to reach, wave crests are going to reach you more frequently. You're trying to like blip, 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 blip. So the bug's still going blip, blip, blip. But these wave crests are blip, 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 reaching you more frequently. Right? Different versions of that. Doppler effect. Change in frequency. Okay. You guys got change in frequency? All right. Got Jonathan, Elise, Zariana, Zach, Luciana. Same scenario compared to the speed of the waves emitted by the bug. The speed of the waves reaching you. Ooh, two winners. It's the same speed wave, same speed. Okay? When those ripples are going across the water, they just go at whatever speed that they go. Okay? It doesn't matter the motion of the source or motion of the observer for that matter. Okay? The speed of the waves is whatever it is. Okay? Do you guys see how? Well, you can kind of see here. Even though I do have this car in motion, and these wave crests are reaching this observer more frequently than they would if the car was parked. Okay? Does, these wave crests, guys, are these still circular? Are they still circular? Yeah, they're still circles. Once these pressure waves have been released into the air, if this is air, they just go at whatever speed they go through that medium, which does not depend on the motion of anything else, right? Like the source or the observer. Yeah, the speed is whatever the speed is. You guys get that? So same speed, different frequencies. Okay. All right. Oh, as the sound of a car's horn passes and recedes away from you, the pitch seems to decrease. Yeah, decrease pitch. All right. And I think it was back on Friday, we were working through this. Okay, well, if you know that's true, then you can figure out how to navigate the Doppler formula, like what's plus and what's minus, right? Because there were some plus minus options there. All right. Doppler effect is change in observed frequency due to motion of the source or observer. There you go. Okay. So in the I can point this out. Okay. In the formula, if the observer is moving, that shows up in the numerator. If the source is moving, that shows up in the denominator, right? And then depending on which way they're moving, gotta navigate this plus or minus. Right? Yeah, so change in frequency, change in observed frequency due to motion of source or observer. Jonathan, Zariana, Elise, Zach, Luciana. If you double the frequency in a vibrating object, its time period. Yeah, it's half. Okay. Okay, so find a formula to back that up. Should be somewhere in here. This works. Right? You see this one right here? Right? So, for example, what if you had 1 beat per second? Is that about 1 beat per second? Right? So then that would be a frequency of what? 1 hertz. Right? Now, what if I cut the time in half? That's pretty close to 2 beats per second. That's perfect. Okay? Guys, if it was a frequency of 2 hertz, what's the time period between beats? Half of a second? Because reciprocals. Right, there you go. Okay. Time period, frequency, you double one, get half of the other. All right. All right. Points. During a single time period, the distance traveled by a wave is one wavelength. Yeah, one wavelength in one time period. In fact, guys, if you divide one wavelength by one time period, that gives you what? What is distance divided by time? Speed? Wave speed? Right? Maybe. I might show up later. Isabel, Zariana, Zach, Elise, Luciana. Kid swings back and forth on a playground swing. What if he stands rather than sits? What's the time period to swing back and forth? Stands rather than sits. Nice. Yeah, would be less time. All right, so here, I'm gonna steal my notes from earlier today. That's fine. Okay. All right. So, guys, a swinging back and forth. That's basically a pendulum, isn't it? It's pendulum. Okay. All right. Now, this last picture I got him sitting down. This right picture I got him standing. Okay. Now, guys, what physical property of the pendulum changed by him standing up? The length. Do you see? Here's which pendulum is longer, the left one or the right one? The one on the left is longer. The one on the right is shorter because we're going from this pivot point to a center of mass. You see it? And over here, ooh, yeah, definitely shorter if he stands up, and then longer when he sit down. You see it? Right. So the length. Right. Now here's your time period of the pendulum: 2 pi times square root L over G. Right. Do you see if it's a shorter pendulum, it's going to be less time to swing back and forth? Right. So let's put it all together. Let's make an animation. Might go like this. Picture on the left. Swing, swing, swing. Picture on the right. Swing, 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 swing. It's kind of exaggerated, but you guys get the idea. Okay. It would speed up. It would be less time with a shorter pendulum. All right. Isabel, Zach, Zariana, Elise, Luciana. Pendulum suspended in an elevator. Oh, I think this was a quiz question. When the elevator accelerates upward, the time period of the pendulum. Elevator accelerates upward. Yeah, decreases. Decreases. Let's take a look here. Look. All right, so here's an elevator. So you're standing in this elevator. Let's make it a big elevator. So you're standing down here. You're watching this pendulum swing from the ceiling. I still got this pendulum going swing, swing, swing. So swing back and forth. Watch this pendulum. Right. Right. Now, let's have this elevator accelerating upward. Accelerating upward. Okay. What does it feel like just happened if you're in an upward accelerating elevator? Do you feel really light or really heavy? Really heavy. You feel really heavy. Like, guys, if you're standing on the scale right here, let's get a scale. Standing on the scale, is the scale reading a huge weight? Like, if the elevator was at rest and you weighed 500 newtons, now if it's accelerating upward, that scale is really being pushed into you. I bet it reads like 600 newtons. You might think somebody turned the gravity up, right? Except the gravity field didn't really change, but you can't really tell the difference. It's as if somebody turned the gravity up. So let's go back to time period for this pendulum is 2 pi times the square root of L over G. That's true, right? Is it good? Except now, if you increase that perceived gravity field, right? And I think on your quiz I wrote this, G plus A or G plus or minus A, something like that, right? Like I said, if you pump up this gravity field here, make this denominator bigger, 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 what happens to the time period? It gets what? Smaller. So if the elevator was either at rest or constant velocity, maybe it's going like swing, swing, swing. But if you're accelerating upward, it's more like right, really fast. Let's go the other way just to extend this a little bit. Because what if the elevator was accelerating down? Let's take it to an extreme. What if somebody cuts the elevator cable and you go into pure free fall? Because if you're in pure free fall, what does it feel like the gravity field is? True. Yeah, you'll be pure free fall. But if you're inside and you can't see the outside world, does it feel like you're an astronaut, like halfway to Mars? It feels like there's no gravity, right? Because if there's zero gravity down here, I got my own extra question. Because if there's zero gravity, how much time does it take to swing back and forth? Yeah, it'd be like infinite, wouldn't it? Right? You'd be divided by zero. What would that look like? So you pull it back, say like 10 degrees from the vertical, right? Now the elevator is accelerating down at the full rate of gravity, so it feels like there's no gravity inside. You let the pendulum go. What does the pendulum do? Does it even swing at all? Nope, doesn't at all. It's just frozen right there, isn't it? It's frozen, right? Yeah. Hence, it would take an infinite amount of time to swing back and forth because it's not swinging back and forth. Right? Makes sense. You guys see how this all connects? Okay. All right. We got Zach, Zariana, Isabel, Elise, Luciana. Observer on the ground hears a sonic boom created by an airplane flying at. There you go. Greater than the speed of sound. Just for completion. Flip it here fast. So it starts with this, but what if this vehicle catches up to the waves and then surpasses the speed of the waves it's sending out? Boom. Looks like this. So what if you're standing right here, right on top of the sea? You guys see the sea for Mach, right? You're standing right on top of the sea. and you've seen the plane go overhead. The plane's already passed. Have you heard it yet? No, because none of these sound waves have reached you. But when they do, they all hit at once. Boom. Right? How about this? Because what if this plane's going just a little bit more than faster than sound? What if it's going like 1.1, like Mach 1.1? So a little bit faster than sound. Would this cone be really skinny, or would this cone be kind of flat like this? Yeah, think kind of flat like this. It would be right. It'd still be a cone, but barely. Right. But what if it was going like Mach 5? I think they call it hypersonic. Right? Do you think this cone gets skinnier? Right? In fact, I bet if you had a protractor and you measured some angles here, you could match and figure out exactly what the speed of the plane was. Right? Do that. If you know one, you know the other. Some geometry there. Right? All right. A sound wave that has a higher frequency has a wavelength that is higher frequency. Oh yeah, nice, shorter wavelength. Right. Back that up real fast with the formula. This is formula here. So speed is constant. Oh, a high frequency is going to be a short wavelength. Here, actually, I want to do some numbers with you guys. Let's do some numbers. Right. Let's do speed is wavelength times frequency. Right. You guys good? Okay. Oh, how about how you guys are hearing me right now? Because what's the speed of the sound waves from me to you? Yeah, somewhere there. 340, I'll call it meters per second. Right. Uh, plus or minus a little bit. Oh, do you think it's possible? Maybe I'm talking approximately 340 hertz, maybe. I think it'd be reasonable. It's probably not a single tone, but you guys get the idea, right? Okay. Guys, if that's true, then what's the wavelength from pressure point to pressure point from me to you? Huh? Yeah, 1 meter. 1 meter. Wouldn't that be? No, folks. Let's double the frequency. I just go up an octave. Go up an octave. They got me like 680 hertz. And I'm talking about 680 hertz. What happened to the speed of sound? It's the same speed. It's the same speed. What happened to the wavelength? Oh, different musical notes, different frequency, different wavelength that are inversely related, but same speed, same speed. Two waves, same place, same time, in step with each other, each had an amplitude of 1 meter. Now, when they constructively interfere, the amplitude is going to be 2 meters, right? Because 1 and 1 is 2. Where's my constructive interference poster? Got it right here. Constructive interference. Right? You guys remember this? Right? Got two. Well, no, let's do my poster example. If I have 2 units tall and 1 unit tall, and they cross over, guys, what's 2 plus 1? 3 units tall. And then you guys saw the video version of this last week. There's more to the story because then the wave pulses just go ahead and cross through each other, don't they? So I got it before, during, and after. Right? Let's do the destructive. Oh, because what if you have 2 units up and 1 unit down? Can you do 2 minus 1 to get this one? Okay. And then, of course, there's more to the story. These pulses go ahead and cross right through each other and just keep on going. Okay. You guys saw that last week too. And we talked about noise canceling headphones. Okay. It's the pressure version of destructive interference. All right. Weight on the end of a spring bobs up and down 1 cycle every 2 seconds. It's like bob, bob, bob. What's the time period? 2 seconds. Yeah, that's it. All right. Here's another question. Guys, what's the frequency? Half a hertz. Yeah, 0.5 hertz. But the time period would be 2 seconds between bobs. All right. That's Ariana, Zach, Isabel, Elise, Luciana. Leaf in a pond oscillates in down 2 cycles every second. That's more like bob, 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 bob. What's the frequency? 2 hertz. And what's the time period between bobs? Half a second. Ah, okay. Here, see if I can draw that out. Okay. So, some paper here. Okay. Uh, say you're standing on a dock, maybe, right? Get a dock going, right? You're standing here, you're looking down to the water, right? And this water, right? Maybe you're watching the waves come in, right? And it's going now. There's a propagating energy wave that's maybe like traveling horizontally, but the water is pretty much just moving up and down. Bob, 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 bob. You're watching this leaf. There's a leaf like right here. There's this leaf. It's doing 2 cycles per second. Bob, 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 bob. Right? So I know frequency is 1 over the time period. So if time period was the frequency was 2 hertz because 2 bobs per second. That's a time period of half a second. It'd be half a second between bobs. So bob, 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 bob. 2 bobs per second. Frequency is 2 hertz. Right. Wave travels 10 meters in 2 seconds. What's the wave velocity? At 5 meters per second. Okay. Guys, think about how units work. If you're looking for velocity, which is in meters per second, that tells you what to do with the units. Right? One of the things to get out of this class, right? How do things work? How do you get meters per second? Well, if you have meters and seconds, probably have to what? Divide or multiply those. How about divide, right? So 10 meters divided by 2 seconds gives you 5 meters per second. Is that right? All right. Oh, last question for the win. For the win. Wave has 2 crests, 2 troughs each second. Sounds like that leaf bobbing up and down. The wave travels 120 meters in 3 seconds. So let's start putting some things together. Go back again. 2 crests, 2 troughs each second. That tells you the what of the wave? Frequency? And that's a frequency of how many hertz? 2 hertz. You guys see 2 hertz right there? So where this F goes for frequency, put 2 hertz. Right? If it's going 120 meters in 3 seconds, ooh, you can get the wave what from that? Speed? Wave speed? Right? And guys, what is that wave speed? 40 meters per second. So where this wave speed is, put 40 meters per second. So you got 40 meters per second at 2 hertz. What's the wavelength? There you go, 20 meters, 20 meters. Okay. Here, we connect this back to the picture I was just doing. Okay. So if you measured crest to crest, you guys see this wave bob up and down, like 2 cycles per second. That's a frequency of 2 hertz, goes right there. Okay. And if you measured crest to crest, right? Well, if you watch one of these crests travel 120 meters in 3 seconds, that'd be a wave speed of, you got 40 meters per second right here. I got a frequency of 2 hertz right here. You guys see I would need a wavelength of 20 meters is exactly what you guys said. You guys see this right here from crest to crest would be 20 meters. Okay. All right. So who won Kahoot? With the bronze, Jonathan. Silver, Luciana. And the gold, Elise. All right. Nice job. Nice job. All right. So let's do some demos. Got a Paul Hewitt for you guys.
Hi, gang. Sound time. If this room were filled with ping pong balls and I had a big paddle and I shook it back and forth, I'd send vibrations through those ping pong balls. Same type thing happens when I strike this tuning fork. This vibrates back and forth and hits the air. The air vibrations, that's what you pick up as sound. Here I have a fork of frequency, same. Watch, listen at me. Strike this one vibrates. Or, as long as the frequencies are matched, I can get the vibrations to cascade back.
You guys see that? You guys see he struck one, and then the other vibrated, and then he stopped the first one, second one kept going, then he stopped that one, the first. So it cascaded back and forth. Here, I'll rewind so you guys can catch that again in case you missed it. Sound cascades back and forth. There's some resonant frequency because the frequencies match.
Vibrations, that's what you pick up as sound. Here I have a fork of frequency, frequency, same, same. Watch, listen at me. Strike this one vibrates. Or, as long as the frequencies are matched, I can get the vibrations to cascade back. It's called resonance, huh? What happens if this fork has a different frequency? Let's try now. Yuck, nothing. I have to have this frequency the same as this to pick up the vibrations from here. That's what happens with a radio set. Your radio signals are coming in and you change the frequency of your radio set so that it matches the incoming frequency. You got it. Physics. Yay.
All right, it's fine. Chase from California.
My name's Chase and I live in California, and I'm gonna try to break this wine glass by only my voice.
So I think that one glass had a certain what you call a resonant frequency, and I think he was hitting that with his voice, right? So let's see if you know, say like the speed of sound inside the glass, and you know the circumference of that glass, right? I bet you could do the physics there and figure out. I bet he was sending a sound wave around that maybe matched some multiple of that circumference. Do you guys think? Right, something like that. So then, as long as he keeps pumping in the same sound over and over, which he was, then it builds up and eventually, it's going to tear down that glass. Guys, can that happen to big structures? Can that happen to buildings? Right. I know a story from here. Please. Yeah.
Military types going across a bridge. Before they hit the bridge, the honcho's going hut, hut, hey, hut, 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 hey, four, or step, 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 step. But when they get to the bridge, they break step, and then like that, and then maybe everyone crosses the bridge out of step. Why? What if the resonant frequency of the bridge is hut, hut, hey, hut? You know what I'm saying?
Could that possibly take the bridge down if everybody's marching in step? Yeah, that's happened before, right? So this reminds me too of buildings can also have a resonant frequency. If you go to University of Florida, one of the buildings they have there is O'Connell Center, called the O Dome. They play NCAA basketball games there. It's a little small arena, right? And what I was told by one of my engineering instructors was that when they were building this O Dome, some engineer ran a check. Okay, well, what's the resonant frequency of this dome? And he did the math and got 2 hertz. Now, guys, why would 2 hertz be a bad resonant frequency for that structure? Yeah, because if you have a whole bleachers full of people, right, and they're all bouncing up and down like, go Gators, go Gators, go Gators. If that's 2 hertz, you got thousands of people doing that. That could be damage to that building. You might even take it down if it, right? So yeah, it's called a resonant frequency. Let's see what else he has to say here about this bridge. Right. Oh, I meant to ask you guys before I play this video. Is anybody in ROTC? Or did you guys learn about this? Right. So you learn to march in step, left, right, left, right. But yeah, exactly what he's saying here. You're told to not march and step over a bridge for this very reason.
You know what I'm saying? In fact, this happened in Manchester, England some years ago. All the troops are following the honcho, and the honcho's counting cadence, and he goes across, hut, 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 and he's ahead, and he keeps going. He's on the other side of the bridge, so hut, 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 and the people, wipe out city.
All right, let's look at a famous example of this. You guys ever heard of Tacoma Narrows Bridge? Tacoma Narrows Bridge. You guys know about this? Maybe? All right, well, what are your physics for? Let's go back to 1940. Right, so 1940, they build this bridge. Let's see, opening. Oh, there's opening day right there. Right now, what they did notice pretty much right away is that the bridge would tend to like bounce up and down a little bit. I'm not supposed to, but so okay, let's have the engineers just keep an eye on it. The cracks are opening up. It's probably okay, I guess, right? So they use that for a few weeks. Yeah, one day that happens right there. That happens. So here's some questions for you guys. Guys, what is that bridge made out of? Concrete and steel? Yeah, you guys think concrete and steel? Yeah, sure is. That's concrete and steel right there. Right. Where do you think the energy is coming from to make the bridge do that? There's a law of inertia. Maybe just want to say at rest, but what's driving it to do that? The wind, exactly, the wind. Hold on to that idea because that's going to come back later, right? So you got this strong horizontal crosswind, it's just blowing, blowing, blowing. Hey, that's like Chase from California and his wine glass. Right? So, whoa, it's just. Let's do some counting here. Oh, there's a. Do you guys see an engineer walking along that nodal line right there? Right now, he did get off this bridge before it collapses, which is going to come too. But his car's parked out there right now. He's checking this out. Let's rewind a little bit and count. Guys, how much time approximately does it take for that bridge to cycle through? Here, I'll count it with you guys. Let's go. 0, 1, 2, 3, 4, 5. I don't know if I counted a little bit fast. Somewhere in the narration, I've got it muted. He says like 5 seconds. It's about what, 4 or 5 seconds? About somewhere there, about 4 or 5 seconds, right? Guys, well, let's round that up to about 5. If it's 5 seconds to cycle, that's the time period. What's the resonant frequency of that bridge? 1 over 5. So like 0.2 hertz, right? A fifth of a hertz, 0.2 hertz, right? Okay, and that's what's driving into that bridge there. All right, so let's fast forward a little bit. You find where this thing falls apart. It's pretty close here. Yeah, he lost his car, but he ended up getting off though. All right, there you go. All right. Now, ooh. All right, so what went wrong? What did engineers learn from this where they don't build bridges like this anymore? Right. And how they fix this? Because part of this is okay. Like you guys see this big old column right here stuck into the water. Like that part's okay. Nothing wrong with that. So they were able to go back and reconstruct this, but obviously they don't want to build it exactly the same. So they don't want that to happen again. Okay. So what's off here? And so, I hit exactly the right frame. Okay. There's information in that frame right there that says what went wrong with it. Right. Actually, maybe I should ask you guys. Does anybody have a guess? Maybe what went wrong with it? They were able to fix. Okay. It's right near the bottom of the frame. You guys see this right here? This is vertical oriented girder, like vertical girder, vertical, vertical. You guys see that? Okay. Here, let's bring this over here to show you guys how to build a bridge. It's not going to fall apart. Maybe I'll see if I can steal some notes from earlier. Here we go. Got some notes from earlier. Okay. So this is what they were thinking when they were designing this bridge and originally building it. Okay. Is, well, we got all these cars going across. Hey, cars, they weigh a lot. That's a vertical force. How do you hold of a vertical force? Well, if you have these vertically oriented girders, that would maximize the vertical load that you can carry, which is true, right? But in the real world, maybe there's in the actual environment, maybe there's other factors they hadn't considered. Right? Like, oh, how about that crosswind you guys were talking about, right? Guys, that crosswind is probably blowing mostly which way? Horizontal. Ooh. And are these vertical girders going to be any good at carrying that horizontal wind? Ooh, not so much. So, how do you fix that? What can you put into a bridge system? They start with a TR. Truss, a truss. Aha! There you go. There's the solution right there. Okay. So all you had to do, I mean, the columns were already set in place. That was all fine. No, they didn't fall apart. Okay. So they went back and built the bridge. Yeah, they just put in a truss system. That truss system right there. Okay. All right, let's talk about earthquakes. Has anybody ever been in an earthquake? Been an earthquake? No? All right. Yes. Yeah. All right. So if anybody ever goes out to California, maybe. So also this showed one of your textbook puzzles last week, I think, mentioned P waves and S waves. When an earthquake hits, there are two kind of waves that are sent out. Now I've heard P and S stand for pressure and shear, which is true because that P wave is definitely a pressure wave. That S wave is definitely a shear wave. I said, right? Like if the ground moves right and left, that looks like pressure. If the ground only moves up and down, that looks like shear, right? You guys said. I've also heard P and S refer to primary and secondary, which also works. Because guess which one of these waves travels faster? Yeah, the P. So which one hits you first? The P, hence primary, right? Right. Which one of those do you think causes more destruction to buildings? Yeah, how about that S right there? That looks pretty wicked. Let's see some video footage from a magnitude 9 quake that hit Japan back in 2011. And so watching this pool, you guys want to be swimming around that pool water right there? That looks like a nice pool. Yeah, I gotta go in for a swim. Right, nothing right there. All right. And then, looks like the P waves are hitting. You see that camera shaking around a little bit? P wave, is that water still pretty calm? Water's still pretty calm, right? You should be swimming around there. Until, oh boy, there's the S waves. Oh, look at that water now. Woo! Slosh City. Ooh. Maybe if you wore a helmet. But yeah, maybe don't be swimming around that water. Oh yeah, there's the S. Right. So you guys saw the P. Now the P's back here. Right. And then there's the S. P and S. Right. Of course, most modern building codes, if you're around the Ring of Fire, right. Let's look at great. Is this on mute? I think. Yeah. Let's check this out. So doing earthquake detection. Now, earthquakes are notoriously difficult to predict. Ooh, I'm going to draw that pretty soon here. Be looking at that. Let's look at some of the seismograph reading. Yeah, you guys see that right there? The seismograph reading? Okay. Now, it just so happened that you're going to play a little of this. An earthquake hit while they were recording this video, just completely randomly, right?
Here's the P, G arrival here, P arrival here, P here. This is New Hampshire. There's a P there. This earthquake, I think, is not in the United States, but it's a pretty big quake. Probably maybe south. This is.
All right. All right. So what's going on here? How do you read those waves, right? And what's the science behind that? All right. So yeah, we got these seismograph stations all over the world. Okay. And how do you construct one of these? Well, we got this big old roll of paper, right? So got this roll of paper here, like this big old scroll, right? And it's just rolling all day, every day. It's like moving, let's say that way. I'm doing a version of this, right? Okay. And I got this pen, like this ink pen right here. Some huge mass. I'll put M for huge mass. And it's connected to the outside world by a coil. I see this big old coil right here. Okay. Now, most days, all day, every day, it's leaving this ink line. It's just a flat line, and there's nothing too exciting about that. Right? Just scroll, a flat line, nothing exciting. Right? When an earthquake hits, the whole world is shaken. Right? The whole world's shaken, except for this pen, because a lot of inertia wants to sit right there, and it's really hard for earthquake vibrations to make it through this coil. Maybe a tiny bit, but not very much. So, and whatever it does, it's not going to affect this pen very much because it's so much mass. Right? So, if you unscroll this thing and you look at it, what's this going to look like? Right? It's going to look something like this. Like, first of all, flat nothing, and then you get this, and then you get something like this. That's kind of what you guys just saw in the video, right? Look pretty much like that. Right? Hey guys, what does this section right here represent? What does that represent? P waves. There's your P waves right there. Okay. And what is this right here? S waves. Okay. Now, if you know the speeds of these waves, which might be regional because maybe it depends on what rocks are underneath the terrain or something like that. Okay. But if you know the speeds and you know the time delay, which you can get from this because you know how fast the paper's scrolling and you know this distance you can measure with the ruler, you guys think you could figure out pretty fast what the time delay is between the P and the S? Right? Right. So if you know the time delay, you know the speeds of the waves, you can do a version of distance equals speed times time. Right? This is one of your textbook puzzles you may have done last week. Right? And you can figure out how far away from the epicenter you are. Right? For example, what if you were right on top of the epicenter? What would this time delay warning be equal to? Yeah, 0. Yeah, there be no warning off. Be nothing. Happy birthday. You just here's the earthquake. Right? You get nothing. And the further away you are, I bet you get more warning, right? Something like that. Right now, you start calling up other stations because here's a station, here's a station, here's a station. Maybe they're like hundreds of kilometers away from each other. Right? Maybe here's our station right here. And we say, okay, this happened like 100 kilometers away from us. We don't know exactly where. We just know it's 100 kilometers away. So I can make a circle with a radius of 100 kilometers. I call up this station. Say, oh, how about 200 kilometers away? Oh, 200 kilometers. Okay. So make a circle around here. It's 200 kilometers. Call this station. Happened about 180 kilometers or so. So make a circle around them. It's like 180 kilometers. Okay? And you keep calling up stations. Right? It's eventually going to converge at one point because that point right there is called the what? EF epicenter. The epicenter. So maybe there's a fault line and some fault went like slipped. There's different kinds of fault slips, but something yeah that initiated that earthquake. There you go. And I'll say so there's a big earthquake hits. It shows up on the news, and they point to a map and say epicenter's right there. Yeah, that's how they know it. Right. Here, got a minute here. Show you guys an earthquake test. So yeah, if you're in an earthquake prone zone, like out on the West Coast or anywhere on the Ring of Fire, they should have building codes that make it really hard to knock down buildings, right? But where do those codes come from? They come from these scientific engineering experiments. So this is a real scale building, like a full scale size building. They got it on rollers and they're accelerating it in certain ways to mimic earthquake waves. All right, there you go. A little engineering test. That's fun. All right, so that's a good place to stop today. And we got, well, we start new stuff tomorrow.